Hey there, welcome back. In the recent videos, we've discussed a number of parameters of circular motion. We've discussed period, frequency, angles and radians, angular speed, and linear speed. Now we're going to cap these discussions by revisiting centripetal acceleration in circular motion and see how that's related to linear and angular speed. You'll remember our earlier discussions about centripetal acceleration, which was the acceleration because of turning or acceleration of circular motion. So if I have an object that's going through this kind of an arc over here, even if it maintains the same speed, so the speed here is v and the speed when it gets here is also v, its direction is changing, so the velocity is changing, and hence there is an acceleration. And we saw that that acceleration has a direction that's pointed toward the center of the curve, hence centripetal acceleration. And we also discussed the fact that the acceleration's magnitude is given by v squared over r, where v is the speed of the object and r is the radius of the circle that it's tracing. So let's now put that in the context of angular speed. So we recently learned that v equals omega times r, and so I can put that value in here and get centripetal acceleration as omega times r, which is v, and I got to square the whole thing, divided by r, and that becomes omega squared r squared over r. One of these r's will cancel, and that gives me omega squared times r. So that gives me two forms of the equation for centripetal acceleration. I can either say that it's v squared over r, or it's omega squared times r, and they are both equivalent. Now let me ask you a question. If I double r, what happens to a? So let's look at these equations and see if I can get an answer. If I look at the first form of the equation, it seems like if I double r, I'm doubling the denominator, so a will become 1/2 of what it was. But then if I look at the second equation, it looks like r is in the numerator, so if I double r, a would double. So which one is it? Does a become 1/2 of what it was, or double? And the more disturbing question that may be going through your mind is, what is wrong with these equations? Which one can I trust and which one can I not trust? Well, both of these are valid equations. They're both correct. And the answer to the original question, what happens to a when r doubles, is it depends. So let's see what we mean by that. So there was a fatal flaw in our logic when we looked at this form of the equation, that a equals v squared over r, and concluded that a would become 1/2 when r doubles. We're making a critical assumption. We're assuming that as r doubles, nothing happens to v. It remains unchanged. And then when we look at the second equation and say that when r doubles, a must double, once again, that's only true if omega did not change. Now, if v and r, or omega and r, are related in some way, where as one changes, the other one also changes, then we can't be sure what to conclude unless we look a little deeper. That's what we're getting ready to do now. Before that, let me just give you one quick example that'll make more sense to you. You know that speed equals distance over time. If I have my car on cruise control and I drive twice the distance, what happens to my speed? Well, you're more familiar with this example, so you would say my speed doesn't change. I'm in cruise control. As I double my distance, the time also doubles, keeping speed at the same value. So that's the kind of analysis we're going to do over here. And I'm going to take a couple examples to do this. My first example is that of a carousel that you'd find at an amusement park. We're looking at it from above, and I've got two people riding it. I've got Jack riding it at the edge, and I have Kathy riding it at half the distance from the center. So this distance, if we call it d, Jack's distance is 2d, or this distance is also d between Kathy and Jack. And the other example I'm going to take is that of a track, a circular track for testing cars. So I got one circular track like that, another circular track like this, and once again the radius of the bigger track is exactly twice the radius of the smaller track. And in this situation, two people are driving the car, Alex and Ben. I'll just call them A and B, and they both have their car on cruise control. Alex has it at 100 miles per hour, and so does Ben. Okay, so given those examples, we want to know how Kathy and Jack's centripetal acceleration relate and how Alex and Ben's centripetal acceleration relates. So let's take one of these at a time. I'm going to go back to the carousel. The key thing that's happening here at the carousel is that as Kathy completes one full circle, so does Jack. They both cover the same amount of angle in the same amount of time. So they both have the same time period. The period for Jack equals the period for Kathy. That's the critical thing with a carousel. And because of that, since we know that omega is simply 2 pi over t, because Kathy and Jack have the same time period, they must have the same angular speed. So angular speed of Jack equals angular speed of Kathy. Further, we know that speed, linear speed, equals angular speed times the radius. So now we can see how their linear speeds are related. So we would have linear speed of Jack equals angular speed of Jack times the radius of Jack. And I can write this simply as angular speed since both have the same angular speed. I don't need specification of whose it is, times Rj. And then Vk on the other hand would be omega times Rk. And since we know that Jack's radius is twice Kathy's radius, I can write this as omega times 2Rk, which simplifies to 2 omega Rk. And since omega Rk is just Vk, this becomes 2 Vk. So this tells us that even though they both complete the same circle in the same amount of time, Jack is actually moving at twice the speed that Kathy is moving at. Okay, back to our business at hand. We want to figure out the angular accelerations. We know that as r changes, v changes. And so we cannot easily use this first form of the equation. We can use it, but for now let's take the easy way out and use the second equation. Since we know that the angular speed is the same for both, it's more easy to use this. So I can set this up to say the centripetal acceleration of Jack is the angular speed. By the way, I called both of these as omega, did not need a subscript. So centripetal acceleration of Jack would be omega squared times Rj, and the centripetal acceleration of Kathy would be omega squared Rk. And once again, by plugging in 2Rk for Rj, I can get a relationship that this is 2 times Ak. So I've concluded that by doubling the radius, the centripetal acceleration doubles in this situation. And that was true because of this critical condition, which was omega Jack was equal to omega Kathy. Now I'm going to leave it as an exercise for you to use this first form of the equation and use this relationship between Kathy and Jack's speeds to figure out the ratios of their accelerations, and you will get the same answer as we did here. So now moving on to the second example, when I have the cars being driven at the same speed, the question gives you the fact that VA equals VB. The speeds are equal to each other. And because the speeds are equal to each other, now I'm better off using this first form of the equation. And I can just, without doing much math, I can conclude that by doubling the radius, I take the centripetal acceleration to 1/2. So I can say that AA must be 1/2 AB. Once again, you can go through the work like we did here and confirm that for yourself, but that's what you would get. And separately, you can figure out their angular speeds, who has a bigger angular speed, because omega is V over R. Omega Alex would be equal to v, both of them have the same v, so I'm not going to put a subscript there, divided by r Alex. And the radius of Alex is twice the radius of Ben, so I got v over 2rb, and v over rb is just simply omega b, so this gives me omega a equals 1/2 omega b, which tells us that even though they're both driving the cars at the same speed, the angular speed of Alex is less than the angular speed of B. And that makes sense because Ben is going a smaller distance. He will cover that in less time. Alex will take longer to cover one full circle. And so it makes sense that his time period will be bigger. And because of that, his angular speed would be smaller. Remember, angular speed and time period have inverse relationship. As one becomes bigger, the other one becomes smaller. So in this case, I conclude that doubling r results in cutting acceleration by 1/2, which is just the opposite conclusion as I had here. And that's because this is true because of the fact that VA equals VB. So the form of equation you use to answer this question depends on the factor that's not changing. And in a real-life situation, if both are changing, if v and omega are changing, so for example, if they were driving their cars at different speeds, then you would have to actually do the math to figure out what's going on, like we did over here. So I covered centripetal acceleration in this slice of physics, discussing its relationship to linear and angular speeds, and used this as a basis of talking to you about how to view equations, how to do proportional reasoning, and when to trust what equation with the least amount of work to answer the questions you have at hand. Thanks.